It's my pleasure to introduce Mr. Ted Fecke. Ted Fecke actually was a SES leader in the Propulsion Directorate with the Air Force. If you remember from Jeff Delaney's presentation, he talked about Otha Davenport. When Otha retired, Ted took over Otha's position. Ted has 27 years of experience developing and promoting and applying advanced materials, life prediction, structural integrity, design methods to aircraft engines. And I will say, even though Ted is retired from the Air Force, today he continues to consult with businesses. His knowledge and understanding of the turbine engine industry is quite high, and his connections are very important. And he's been helping to promote and continue to promote various technologies for insertion into aircraft engines. It's my honor today to actually introduce him and to have him participate in our presentation on laser peening. He's going to talk a little bit about his perspective and knowledge relative to the application of residual stresses. Ted, thank you for joining us, and go ahead and start your presentation.
Yeah, David, just not that I want to get credit. I actually spent 37 years in propulsion in the Air Force, and now I've done another 10 afterwards. So I've been in propulsion for 45 years. And pretty much held every job in the Air Force, from science and technology to acquisition to sustainment. So
thank you, Ted, for that correction. Sorry about that.
No problem. So let's get to the next chart. So what I want to do today is kind of review the history of residual stress in turbine engines. We've had a lot of successes, thank goodness, because we've had some major challenges that we wouldn't have been able to overcome, and to kind of highlight those challenges in our application of residual stress. And then I want to kind of push us into where I see the future critical challenges or critical technologies, a very quick payoff, and then I'll just summarize. But to kind of give you a bottom line up front, one of this has been a passion of mine for probably 20 years now, is the improvement of residual stress modeling is critical for us to be able to take life credit of residual stress in turbine engine components. So you're going to see as we go through this, that's a theme. And I think the good news is, I think with all of the technology evolutions that have occurred, integrated computational materials, engineering, and all the other tools that are out there, I think we are ripe to be able to pull this off. And if we can, we'll really be able to enhance our capabilities. So next chart. I always like to start, when you start talking about residual stress, I know pretty much everybody on the line kind of gets what a residual stress is, but for turbine engines, it's like everybody else. It's, it's the equilibrium. Once you do some kind of deformation to a surface, it's the equilibrium stress that must be applied to get equilibrium loads out. And, examples of those you can see on the bottom half of the chart. And from a turbine engine point of view, we pretty much can experience all of those: mechanical, thermal, phase change, welding, and thin films layers for materials with different thermal and crystalline properties. Think of a thermal barrier coating as a great example of that last one. So all of those examples do exist in a turbine engine. What I'm really going to talk about today is the mechanical side, but ultimately the tools that we developed need to be applicable to all of these. And some of them are much shorter putts, so to speak, like phase change. We're pretty good at that. Thermal, we're not too bad at that. Welding, we kind of have an understanding of that. It's the mechanical and the thin film is where we really are struggling. And we have tools. I'm not going to say that we don't have some tools, but it's our ability to accurately predict so that we don't have to go through a very laborious testing program of multiple years and, many, many millions of dollars to be able to take credit. So that's the kind of residual stress we're talking about. And then when you get into residual stress, specifically from this mechanical side, there's kind of two areas I kind of put these into. One is shot peening, or you could do whole cold expansion. They have positive effects. We know that, and are especially valuable on high strength alloys. I will tell you, shot peening is used today as an enhancement, as what I would phrase as a durability enhancement, but there is no life credit taken in a turbine engine application. We do it on pretty much every disc. Most of the airfoils will be shot peened, but there is no life credit taken because of the difficulty in predicting it. And then conversely, or the alternative approach of running a test program is too expensive. But it is used because it is relatively low cost and we know its goodness. And, the one thing we have figured out is when we do want to take some kind of an enhancement or fatigue strength, cold working a hole, like in a disc, bolt hole in particular, does provide greater potential than shot peening. And we do have discs that fly today that are cold hole worked expanded, but we go through a very extensive test program and kind of limited analysis. The other major area, which is what this conference is really focused on, is laser shock peening, ultrasonic peening, are the high intensity kind of processes. The bottom line is they give you this deep compressive residual stress layer in the surface, and that ability for this deep residual allows us to take a life credit, but there is a pretty substantial cost associated with it, both production as well as qualification. And I will just say now that all three OEMs have LSP type application components that are in production that are taking a life credit, but they also had a 4 to 5 year qualification program, and that probably translates into about a $4 to $5 million investment. So that's just on the low end. So the bottom line is in today's turbine engine, shot peening, we use a durability enhancement. When we go after the higher peening enhancements like LSP, it does work. It has worked. We can take the life credit, but it's very expensive to implement, and the production cost. Now, the good news is the production cost is coming down greatly because of people like LSP So what we've got to really focus on is how do we get that EMD cost, engineering, manufacturing, and design. Qualification is another phrase to use for that. The good news is one of the boogeymans that's existed when I started working turbine engines in the early 70s. I mean, we had residual stress then. We used a pre-spin disc for life enhancements. And, but there was always this, well, what about stress relaxation as a function of time? And the good news here is as you can see, there's kind of three ways you can get that stress, a residual stress to relax. You can do a tensive or compressive overload, cycling, loading near or above the endurance limit, or thermal relaxation. And really for us, the main one is number 3, the thermal relaxation. This is an area that has been extensively studied in the turbine engine community. I would say there's probably 30 to 50 government studies that have occurred in this area and have really given us the confidence that with the current tools that we have, it, in my opinion, allows us to kind of manage the boogeyman of relaxation. So if you kind of focus more succinctly on the LSP applications of where we're at today, we've got new airfoils. Like I said earlier, all the OEMs have new airfoils that are being LSP'd, mainly in the fan section. The success of them has been phenomenal. I'm trying to remember, but I think we've only failed 1 or 2 airfoils, and we've got hundreds of thousands of airfoils that have been LSP'd and gone through a lifetime. So the success of the LSP application to airfoils is overwhelming. There's always this cost challenge, and I think we have kind of turned a corner on that. People are starting to work, newer systems and to be able to get that cost down. One of the things we're just starting to work on are repaired airfoils. So if you think about, I have an airfoil, it's LSP, I get a ding, and classically what you do with that airfoil, it comes to depot, and to reduce the stress concentration of that damaged area, you will do what we call blending. So you will take the stress concentration from nominally maybe an 8 or a 9 down to 1 to 2. Well, when you do that, you're machining. And so when you machine, you're obviously machining into an area that was previously residual stressed. And so what the military is currently doing is, by and large, they replace most airfoils that where the damage area is great enough in the LSP area, and not go in and blend it, because the question is okay, when I did that blending, how much of the residual stress did I lose? How can I reapply residual stress affordably? So this is another whole new area I see coming forward. That's kind of a follow-on to our long and very successful new airfoil applications. We know it works for vibration control. If you have mistuning, is mainly associated with a component called a bladed disc. Advanced engines today in the military side, they combine both the blade and the disc into one structure. And that one structure normally generates what the vibration community would call mistuning characterization. And that mistuning can be modified. Very simplistically, what happens is in mistuning is all of the vibration energy can end up going to one airfoil versus being, before it was kind of spread out through all of the airfoils because of the joint that existed between the blade and the disc. But we have been able to prove that we can modify this mistuning characterization. Nobody has used it in production. The one thing we do know that you've got to really manage the tensile stress field that you generate and the mode shape, because there will be an interaction and you don't want that large tensile stress to occur where your mode is got a high strain to it. And I do know of one engine application where it's been successfully used on fretting fatigue. That's where you've got a dovetail in a disc application and it's rubbing, and you go in and LSP the dovetail to prevent fretting fatigue. And it's been successful, but again, cost and the application challenges still exist. So, and then just the other ones that we've kind of looked at that haven't really been used at all, but are out there on the technology side. That should be bolt holes and stress concentration draw designs, or we've looked at peening forming. We have a lot of two-dimensional and bodies of revolutionary kind of structures, and looking at peen forming that can be done, has been proven to be able to be implemented. But again, we haven't been able to push that ball across the goal line. The last one, which is probably not as big of an issue, but it's one that at least is in the designer's toolbox, is stress corrosion cracking and hydrogen-induced cracking. We have proven that LSP does improve both of those relative to that type of mechanism. So LSP has got some good examples that are working, some things they want to go apply, and some things that are still back there in the cupboard, still wanting to be worked on. The thing I want to kind of get your kind of thinking about is to get this life credit. So in the Air Force, Mill Standard 3024, which is called PSIP, is the design system that you use when you're designing a military engine. In the FAA, it's called the FAR 33. And the bottom line is they allow you to take a life credit, mainly for LCF. You can't use it on crack growth. NDI development is critical if no prediction system has been developed. And bottom line is there's limited NDI subsurface that's not destructive. So since there is limited subsurface NDI, the industry has been driven by the specification documents to be focused on prediction systems, which still have some limitations, which is why current handles handle residual stress as a margin of safety. Now, the deep residual stress on LCF, which we've already kind of talked about, again, going back to Mill Standard 3024, you can kind of see the section there. And it does allow LSP and LPB if you've got validation data that exist. And that's where I was talking about this 4 to 5 year program and 4 to 5 million. And it does allow you to, the other thing is it's got to be, if you do have a prediction system, it's got to be applicable to all the detrimental effects in regions from the treated area, like LCF, HCF, stress and creep rupture, and so on and so forth. The good news is, in Mill Standard 3024, if you get approved with LSP, you are allowed 100% of the goodman. Now, if you don't have LSP, you're only allowed 60% of the goodman in that. And so that becomes a critical design area when you're designing an engine and that first stage fan, and you look at what's the allowable FOD stress, and you say, well, if I've got LSP, I'm allowed 100, but if I don't have LSP, I'm only allowed 60%. And you can see that's a monumental enhancement, but you also have to be driven by what's this cost to get it through validation and then again into production. So in my opinion, and it's been a crusade of mine, predictive residual stress benefits to get life credit, we're going to need something similar to what was called the high cycle fatigue program, which the Air Force and industry undertook in the late 90s through the early 2000s time period to be able to pull that off. The other thing is if you go back, so there are kind of two documents that really control the design for military engines, Mill Handbook 3024 and Mill Handbook 516C, which is the airworthiness document. Section 7 is propulsion. And again, it talks about LSP and being able to take 100% Goodman allowable. And it kind of walks you through when you take these surface enhancements, you got to be able to predict, or you got to also do the normal life prediction, and substantial verification is required, requiring specimens all the way through full components. It's one of the few areas in 516C section 7 that really requires full components. Usually it's just specimen based, but here to get 100% Goodman, it does require full components. The good news is we have done it and it's been very successful. So that's kind of where the airworthiness and the design side from the military sits today, and why an enhanced modeling system is required. So where I'm coming from, future challenges, I see pre-spinning of disc. We pre-spin disc today like we used to back in the 70s. Large commercial disc, especially HP turbine disc, are pre-spun. But they get no life credit. They're doing them so that they control expansion, so that they can machine to tighter tolerances to improve performance. But again, the challenge is to get full life credit is being able to do that cost effectively, the NDI and modeling. LSP applications of airfoils, bladed disc, and disc. We've got to be able to get life credit. And in my mind, cost is always a challenge. We'll never be as cheap as shot peening, but we should be able to greatly reduce where we're at today. I think the ability to look at variable intensity, I think, is critical, and our ability to enhance that will directly enhance our affordability. This NDI capability, I'm not as bullish on our ability to do subsurface NDI measurements. I am bullish on our ability to do modeling, and I think the time is right to go do that. This is just kind of a problem statement around pre-spinning. Disc failures are catastrophic. Residual stress is a key characteristic of a disc performance. If anyone's ever modeled a disc, you quickly get that out. And then, of course, as it's operating and spinning, you expose it. And as I said earlier, pre-spinning is mature. It's used today, but no life credit is taken. It's only used to control the expansion of it so that they can achieve tighter tolerances. Well, once we get a modeling system developed, we'll be able to set how much pre-spinning we do and be able to quantify life potential, life enhancements. So when you look at the future of residual stress modeling challenges, I see modeling and measurement accuracy. There are going to be different levels of accuracy are going to be needed depending on the application. So you've got a bulk residual modeling, which we're pretty good today. Measurement accuracy, you can do surfaces. When we do heat treating and machining today, we pretty much can get that residual stress. Service dimensions, we're pretty good at that. Dimensional stability, that's really what people would refer to as the hot profile versus the cold profile. And then the bottom line is lifing. And that is the one area where we really have got to improve our tools so that we can better predict this improvement that residual stress will give us, so that we can, and it has to be both in the initiation and propagation. And we're going to need to be able to take those models and also incorporate both tensile and creep, because obviously in a turbine engine, you're spinning, you're exposed to air, so there's a tensile stress. And because it is generating combustion products, it's going to be exposed to temperature. The modeling enhancements are also needed to incorporate these data to be able to make this a physics-based tool. It cannot be kind of a regression type model. If that's the case, we're never going to get there. We're going to have to be able to incorporate it as much as possible from first principles, or at least a reduced order model type approach. And we're going to have to also be able to interact microstructure features, because that is an element that becomes critical when you start to want to incorporate a life enhancement around residual stress. And validation of any residual stress predictions, it's going to take quantitative life enhancement. It's going to take a subscale and full scale components. And in my opinion, what we want to do is not have this. I don't believe any one OEM or government can kind of cover this cost directly. We want to figure out how to pull this off across the industry because everybody would benefit, and it would go across the complete supply chain. So there's some major benefits out there with the 5th generation overhaul cost about 3 to 4x the 4th generation. We've got some weight challenges in our 6th generation engines. Both commercial and military benefits would be result from this kind of life enhancement. The engine business model is changing from selling spare parts to a PHM activity. So it is one that I think is a win-win for both the military and commercial. And I think it'll allow us to provide fixes to both current and current field issues that do pop up. So the elements of this residual stress prediction, I think it's going to take a multidiscipline approach. It's going to take both materials and design. I kind of talked about this integration of integrated computational materials engineering and finite elements to predict the subsurface residual stress. Remember, I've kind of stated a couple times, I'm not aware of any ability to predict subsurface residual stress accurately without doing some kind of destructive. Good news is there are optical rotating strain systems that are starting to be developed. And so that really kind of opens up our ability to kind of make that viable so that we can get the real rotating optical or rotating residual stress. Probabilistics technology has continued to evolve, both the FAA and the military. So all of that comes into play. And so our ability to work all of the elements required for a residual stress model development and apply it to, LCM, HCF, LCF, fracture mechanics and burst, I think we are ripe for that application. And it'll be applicable to titanium, steel, and nickel. The good news is the engine guys aren't the only ones looking at this. ASip stands for Aircraft Structural Integrity Program. The aircraft guys have been working along with us. They do not have a system yet for LSP, but they have been working for the cold hold expansion. Again, they are focused on trying to get improved fatigue life and fracture critical components. And then once they get that done, they want to move to LSP and low plasticity burnishing. So I don't think it's just a propulsion enterprise. It would be propulsion in aircraft. And so that's why I think a multi-government industry activity is needed. ASIP's challenge to residual stress, they follow what I would call is the standard building block going forward, and start with simple shapes, be able to predict, and then leading all the way up to fleet. So that's kind of their approach. They have started to dabble. They have completed the cold hold work expansion in 2021. They are starting to try and figure out how they're going to handle the aircraft side. But the good news is this is a propulsion and aircraft focus. So it's not, we should be able to pull this off both technically as well as financially. And then just to summarize, The history of residual stress in turbine engines is rich. Shot peening has been around forever. Prespinning we did in the 70s and LSP of airfoils has been very successful. The determination of the peening credit is critical and not straightforward. Subsurface crack growth is a critical challenge, both from a measurement and modeling. And life credits can only be taken if you've done extensive, and I underline, can't emphasize the word extensive, testing. Like I said, 4 to 5 years, at least 4 to 5 million. It's probably more like 10. Airframe and engine management, like I said, are both working it, and that's to move it into what I call prime reliable, not a durability enhancement, but prime reliable. And my opinion, to pull that off, a major new initiative across the military and industry is needed. So with that, I'll take any questions.
Specific alloy.
Thank you, Ted. Appreciate your review and the challenges and where we stand today in terms of adding compressive residual stresses to turbine components. I just want to let everybody know we've run a little bit long today. We're kind of on this talk, which is okay at the moment, or we're waiting for our next speaker to show. So in the meantime, I have a couple questions I'd like to ask Ted. I know from the discussions we've had, Ted, modeling is an important element in really kind of beginning to help accelerate the implementation of laser peening or residual stresses in turbine components. From your perspective, do you think these models can also be used to help in terms of implementing or accepting life credit, and what is needed to make that happen?
Well, yeah, I think the models are critical to get like I said, you can get life credit just through testing, but because you can't predict it, then you have to test all kinds of different scenarios. You got to test specimens and subcomponents and components. And then you've got to look at, new versus old. So it just becomes a very complicated validation program, which I believe can be not completely, but greatly reduced with a tool that'll do two things. Number one, allow us to better predict how to process it, what processing is needed to get the stress field we want, and then given that stress field we want, to be able to predict what kind of life enhancement we would see. And once we have that, then the validation program would be very straightforward. It mainly would be some specimens and maybe some components. Probably the best example I can give is when the Air Force went to a damage tolerant design for turbine engines for disc in the 70s, we used to spin every disc that we designed damage tolerantly because our crack growth prediction tools were not that great. And so that became a major element of every engine design and manufacturing development program. Well, I can tell you now that the last two engines that we have built new, we have not spun a disc to validate the damage tolerant designs because we believe our crack growth models are good enough that we don't have to do that we can use those models, predict what our damage tolerant is, and we've been successful at being able to use those predicted numbers in the field, and we've been proven right.
Okay. So I guess maybe with, there's a lot of data that's been generated in terms of validating the application of residual stresses. Do you think that data could be used to help support the modeling effort to validate the models, to give them? Can the past data from the physical testing on the component or coupon level be used to help build some level of confidence in the modeling prediction capability, which could then move forward to maybe implementing on new components. Would you see that as an approach to helping build out the models?
I do, David. I think you're right. There's a lot of data out there, and as you know, probably better than anybody else, it's that data becomes highly proprietary, and not easily shared, kind of thing. But I mean, to answer your question succinctly, that data is valid relative to substantiating the models.
Okay.
Now, what we did under HCF to avoid the proprietary nature, we generated, I'll say, totally government owned with industry participation, data that could be shared across all of the OEMs. But to answer your question is, yes, I think it's all valid.
Okay.
The challenge is how much of that could we really use? Because more than likely, the OEMs are not going to produce the model. That's not something they do today.
Right.
They would expect people like LSP and others to develop that. Now it's a question of, how do you get that validation? Now, some of it is government owned, but
Right.
most of it is not.
Yep. Okay. Well, appreciate the answer.